Chapter 8, Substitution Reaction. In the previous chapters, we studied the relation between a metal M and a ligand L. And the study of the bond ML was very important in order to know if M can receive another ligand L prime or if M can release the ligand L. So now we will start the reactions, the main reactions in organometallic chemistry, and then we will study the mechanism and the catalytic cycle at the last chapter. Ligand addition or ligand dissociation. It's simply the formation or separation of a ligand, usually Lewis base, to or from a complex. We have a metallic center, we add a ligand L to form the bond ML. In thermodynamics, if the ML state is less stable than the initial state of M, so the addition of this ligand is practically impossible. So this is an association of the ligand or ligand addition. The dissociation of the ligand when ML release a ligand L to form M plus L. By the same way, the state of final M should be more stable than the initial state of ML. To note that the addition and the dissociation of the ligand are reversible. So for example, when M add a ligand to form ML, this is a reaction in the direction of formation of ML. At the same time, the reaction could happen in the inverse direction, in direction 2, where we have dissociation of the ligand. But as in equilibrium, we have one direction that is more favored than the second, and the favoring of the direction or the shift of the equilibrium is determined by several factors that will be studied in the next slides. What are the key characteristics for this reaction? For example, in the ligand addition, we should have a vacant site. And in the ligand dissociation, we open a vacant site. The ligand addition increase the electronic counting by 2 without changing the oxidation state of the metal. And the ligand dissociation decrease the electron count by 2 also without changing the oxidation state. Ligand substitution. A substitution reaction is one in which an existing ligand on a metal center is replaced by another ligand. For example, MLN plus XP gives MLN minus XPX plus XL. So in this equation, in this reaction, the ligand L is replaced by the ligand P. This is only possible if the bond MP is more stable than the bond ML. The substitution reaction depends on several factors. Factor 1, on the electronic count of the metal complex, if the complex is saturated or not. If the complex is saturated 18 electron complex, it could not add a ligand P directly. The complex should dissociate a ligand L, then association of the ligand P. And if the complex is unsaturated, so we have a vacant site, the ligand P can be bound directly to M, and therefore after binding this ligand to M, we have dissociation of ligand L. The second factor is that affect the substitution reaction is the existing ligands on the metal. We have to know that the nature of P is very important. If P is neutral, it can replace only a neutral ligand, L. And if P, for example, is anionic, it should replace anionic ligand, L. The factor 3 is the steric and electronic properties. In the case of methylphosphine, we studied the Tolman-Kohn angle, and we deduced as the phosphine is bulky group, it can be dissociated easily from the metal M. To note that a mechanism is a theory deduced from the experimental data, and the experimental results are facts, so the mechanism is based on this facts experimental. And we can never prove that a mechanism is right. We can prove if it's wrong. So the substitution depends on the nature of the complex. If the complex is saturated, it should release a vacant site, then we add a ligand, so the pathway is dissociative substitution. And if the complex is unsaturated, so we have a vacant site, we can add directly the ligand L, then we have dissociation of the ligand L prime, so the pathway is called associative substitution. We have another factor that affect the substitution or the addition, which is the geometry of the complex. In this example, the rhodium is rhodium 1, is D8 and is 14 electron, and the geometry is trigonal planar. So we have vacant site on rhodium that can receive a ligand from the external. The addition of the ligand CO, for example, will transform the geometry of the rhodium from trigonal planar to the square planar complex, which is more stable geometric form. So in this case, the addition is favored. Consider the dissociation of the rhodium complex, rhodium triphenylphosphine chloride. Rhodium will dissociate a ligand due to the steric factor. The triphenylphosphine is a bulky group and we have 3 groups. So this structure is unstable. In this case, the rhodium complex will release a triphenylphosphine ligand to open a vacant site. If this vacant site remains empty, so the triphenylphosphine ligand dissociated will be bound to the rhodium. In this case, if we want to make a stable structure of the rhodium complex, we have to add another ligand in the system which is not bulky group that can occupy this vacant site, and in this case we prevent the reassociation of the triphenylphosphine or rhodium complex. In the second complex, we have bidentate ligand. So ruthenium could not release a bidentate ligand which is the dimethyl ethane phosphine, since the polydentate ligand are bound strongly to the metal center. So, the structure is also bulky due to the presence of these groups. In this case, ruthenium will dissociate Cl- to open a vacant site, and the complex is positive in order to maintain the oxidation state of ruthenium unchanged. If this vacant site remains empty, Cl- will be bound to the ruthenium and we will obtain the first structure. So by the same way, we have to add anionic ligand that make this structure less steric. Depends in large part on the electron counting of the metal complex. For 18 electron complex, we have dissociation first of a ligand, then association of another ligand. So we have dissociative substitution. In the dissociative substitution, one of the existing ligand on the metal M will open a free site or a free coordination site. To note that this free coordination site should be filled by the ligand, or if not, the dissociated ligand will be associated to this site and reform the initial complex. Consider the example of molybdenum carbonyl complex. This is an 18 electron saturated complex, so it cannot receive a ligand. It should lose a ligand first, minus CO, open a vacant site or a free coordination site. So this is an unsaturated complex of 16 electrons, and the oxidation state of MO remains the same. Then the ligand added will occupy this vacant site to give the p-methyl MO carbonyl complex. So the global reaction is a reaction of substitution of CO by trimethylphosphine, and this substitution is in the dissociative pathway. The dissociative substitution can also occur in complex of 16 electrons. In very unusual cases, lower electron count systems complexes. And these cases involve bulky group that will create a steric effect and can block the open coordination site. For example, in this complex of nickel, this is unsaturated complex of 16 electrons, so the nickel has a vacant site that can receive directly external ligand. But due to the presence of tris-cyclohexylphosphine ligand that is bulky, this bulkiness or these bulky groups will hide this vacant site. So in this case, we could not add a ligand directly. So the reaction will follow the dissociation to open a vacant site, then p-methyl-3 is added to occupy this vacant site. To note that this substitution is possible only if the bond Ni p-methyl-3 is stronger than the bond Ni p-cyclohexyl 3. The steric factors affect the dissociation of the ligand or the addition of the ligand. So it affects the reaction of substitution. Bulky ligands occupy more space around a metal center and can block the incoming ligands trying to access the vacant site on a metal. So the ligand addition is, is not possible in this case. Due to the steric hindrance, some complexes are also more often to dissociate to relieve the steric strain. Consider, for example, the reaction of dissociation of a phosphine from a complex NiPr3,4. As Kd increase, the constant of dissociation increase. That means the complex is not stable and it can dissociate a ligand easily. According to this table, the cone angle is the greatest for triphenylphosphine. That means triphenylphosphine is the bulkiest group in the family of phosphine ligands given. So triphenylphosphine can be dissociated easily from the complex NiPr3,4, and therefore the dissociation of triphenylphosphine has the greatest Kd. But at the same time, triphenylphosphine in the series of phosphine ligands is the best donor. So the bond Ni-phosphine is the strongest. That means p-phenyl 3 cannot be dissociated easily from the nickel complex. So in this example, we have two factors. The donation of triphenylphosphine should give low dissociation, and therefore Kd should be the smallest. The second factor, triphenylphosphine, is the bulkiest group, so Kd should be the greatest. According to these two factors, the experiment proved that the most important factor that affect the dissociation of the ligand is the steric effect. Consider the substitution reaction of Cl- ligand by Br-. First of all, Br- can replace Cl-, since Cl- is more electronegative, so it's less donor. That means the bond platinum Br should be more stable than the bond platinum Cl, and the reaction of substitution is possible. Due to the steric groups present in this complex, the vacant site is not clear. So Cl- could not be added, Br- could not be added directly to the platinum. In this case, the platinum complex should release first a Cl- ligand to open a vacant site, then Br- is added easily to give this complex. So from platinum Cl to platinum Br, this is a substitution reaction, but the pathway is dissociative. In organometallic chemistry, we use always solvents, and the solvents are in general Lewis base solvent. That means they can be coordinated to the complex. So we have another pathway. If the solvent is more donor than Br-, so the solvent will occupy the vacant site to give a bond which is platinum solvent. And if the solvent is weak coordinating, so it will be coordinated to the vacant site, then is released. So this addition of the solvent ligand is reversible. So the 14 electrons is 3 coordinate intermediate, almost immediately coordinated by a solvent molecule to produce the solvated 16 electrons. The solvent is usually weakly coordinated and dissociates to produce the 14 electron reactive intermediate. The coordinating ability of the solvent can affect the reaction. The presence of lone pair, as we said, and electron-rich donor atom in the solvent usually makes it better ligand than Br-. So the polar solvents are usually quite good for involving charged species. For example, if we use a polar solvent, the dissociation of Cl- is more favored since Cl- ligand is charged and can be soluble in the polar solvent. In case we use in this reaction a non-polar hydrocarbon solvent, Cl- could not dissociate since Cl- would not be soluble in the medium which is non-polar. So in this case, instead of releasing Cl- ligand, the platinum complex should release triphenylphosphine ligand. In this table, we have some coordinating solvents, some common coordinating solvents, which are in general oxygenated solvents because the oxygen is not good sigma donor, so these solvents are not good coordinating ligands. Some interesting properties of the solvents used. First, avoid oxygen-containing solvents due to the reactivity of early transition metal towards them, but this is to say that oxygen coordinating solvents are weak donor. Water is not a common solvent in organometallic chemistry since most of the organometallic complexes, for example, the metal-alkyl complexes, are basic enough and will readily react with water. In organometallic chemistry, we prefer to use non-coordinating solvent in order to avoid their addition to the vacant sites obtained by dissociation of a ligand. Saturated hydrocarbons like hexane are a classic solvent, but they are not coordinating. When using these solvents, we may face a problem, which is the solubility of the organometallic complex in hexane, for example. Arene solvents coordinate via their pi systems, so they are not bound strongly to the metal. A common, less coordinating solvent, but polar solvent would be the best solvent used in organometallic, and this is the case of the dichloromethane, CH2Cl2, which is one of the less reactive chlorocarbon solvents. Chlorobenzene is another non-reactive solvent, but somewhat polar solvent. So in conclusion, in organometallic chemistry, according to our reaction, in general, we have to use solvent that is not coordinating or weakly coordinated, and second, that should dissolve the organometallic complex initially. Another factor that affects the dissociation of a ligand is the trans effect. The trans effect was studied in the previous chapters. Two sigma donor ligands in transposition will weaken each other, so that dissociation is easier. Two pi acceptor ligands in transposition will weaken each other, so the dissociation is always easier. One ligand sigma donor and another ligand which is pi acceptor will strengthen each other, so the dissociation would not be, the dissociation of the ligand would not be easy. Consider the reaction of dissociation of the ligand Cl-. Cl- is trans to a ligand L sigma donor, which is a stronger sigma donor than Cl. So the presence of L trans to Cl will weaken the bond platinum Cl, so Cl- can be dissociated easily to open a vacant site. Then the addition of a coordinating ligand will occupy this vacant site. This is the pi acceptor trans effect. The cis effect. The cis effect is less important than the trans. In this example, L is sigma donor, which is cis to Cl-. So L is more sigma donor than Cl, so it will affect the stability of the bond platinum Cl, and Cl- will be dissociated easily. But this effect is not so important. Associative substitution. The associative substitution, as we said, occurs with the complex that are not saturated. So it first occurs by ligand addition to the metal complex, then followed by dissociation of one of the ligands present on M. And this is typical for unsaturated ligands. Consider the complex of rhodium, which is 16 electron unsaturated complex. The presence of the phosphine p-methyl phosphine 2 ligand is not so bulky as a triphenylphosphine. So the vacant site in this case is clear. P-methyl 3 can be added easily to give 18 electron saturated complex. Then according to the solvent, we can have two types of dissociations. If you use, for example, a polar solvent, in this case, Cl- will dissociate. And if we use non-polar solvent, we have dissociation of the phosphine ligand. CP ligands in substitution or ACDC ligands. If we have, for example, around the metallic center, a complex that can change its hapticity. For example, if we have CP around M of hapticity hapto5, the CP can transform the hapticity from hapto5 to hapto1 So it will release the place for the addition of 4 electrons, as shown in this example of rhenium. We will add 2 p-methyl-3 groups. The p-methyl-3 groups could not be added since this complex is saturated. So the CP will change its hapticity from hapto-5 to hapto-3, and it releases the place for 2 electrons to be added. So the first p-methyl-3 is added, then the hapto-3 is transformed to hapto-1 to allow the addition of the second p-methyl-3. By the same way, if we have hapto-1 and we have vacant site, the ligand ACDC can increase its hapticity in order to block this vacant site. And this is useful when we want to use a vacant site occupied by the hapticity factor, and then we can release this vacant site by changing the hapticity in order to receive a specific ligand.